problem at all. The topic of the first lecture is divided in two parts. The first part is more theoretical and we can say academic, the classical problem of reconfiguration of the distribution network, so the topology that can be changed in order to adapt for the operation, so the actual operation into the network, or also needs to be changed because something was faulted. So we have a fault into the network, so we need to reconfigure, to readjust the topology of the network in order to maintain the service as much as possible for all the users. The second part of the first hour, it is devoted to show something very practical, so at the other extreme. So some results of a test of a power station that was directly connected on the primary bus of a substation, so high voltage, medium voltage substation. It is a combined heat and power unit, and the test was to open the circuit breakers that connects the substation with respect to the high voltage grid, maintaining in a island condition the power station and part of the distribution network, the 15 kilovolt distribution network of a city. By using, for the monitoring and for the disconnection and reconnection, phasor measurement units. So I will start with the first part, that is now I need to understand again. I don't know if it is connected. Yes, probably yes. I can also use, but it is not. I can use this. But I can use this. Okay, so I will stay. Please interrupt me anytime so you see something of interest, or if you want to add something, or it is not so clear what I mean. This was the first slide, so the problem of the reconfiguration that I have already seen. I mean, the objective function. The typical objective function is the reduction of the minimum losses. Obviously, the same approach, the same model can also be applied by changing the objective function. Okay, so it is a classical topic of interest, and what is the approach? Since it is an academic topic and so on, there are many approaches in literature applied for this problem. And I would like just to illustrate to you a method that uses a solver, a linear programming solver, mixed integer. So we need to formalize, to represent the problem, the minimization of the losses, taking into account the radial configuration as a mixed integer linear programming model. What are the advantages? The typical advantage is that nowadays the solvers that are available for the solution of this kind of problems have a very good performance with respect also to the past, so they can solve problems with many integer variables also of reasonable dimension that can be applied in the practice. The other advantage for the mixed interlinear programming model is that in general, if the so-called gap, so the difference between the primal solution, the dual solution is small or zero, quite small, I mean, this solution is unique, so every time provides the same the same solution, and the timing of solution are a little bit known in advance. So we have no problems. So they are, I mean, in general, appreciated these properties by the people in the operating room that needs to use these tools and so on. So this lecture describes the mixed interlinear programming model that directly incorporates the typical operating constraints of distribution networks, taking into account the presence of embedded generation. Here the difficulty is, I mean, it is just to represent in a linear programming model the non-linearities that are associated with the problem, the square of the current, for example, or the power that is the product between the voltage and the current and so on. So I will... This is the structure of the presentation. So problem formulation, the mixed interlinear programming model, so the objective function and line current constraints, bus voltage constraints, network equation, and also these constraints that is typical for the distribution network, at least in many cases. We want that the distribution network has a configuration that is radial, because it is a little bit simpler to design, for example, the protections and the selection of the protection and so on. So we also include the radiality constraints, so there are no loops in the final solution, although in the configuration there are loops, because we need to re-energize, for example, some part of the network when there is a fault. And okay, some illustration, implementation, illustrative examples. For these examples, here it is just the comparison between the results of the model and the results that are obtained already in literature. So we know already what is the optimum, or what is the optimum that is already found in the literature, and we can test if this model can achieve the same result and which is the performance. So I will just illustrate the problem formulation. That is we want to know which branches of the network put in operation, and which are the branches that are open in order to satisfy completely the demand into the network, so satisfy all the users, and with that the minimum, thank you so much. Thank you. The minimum losses. So which are the branches that are on and off? So the branches on and off, so the configuration is U. So it needs to be included in this set of all the configuration that are radial. So this is limited just to the radial configuration. We want to just take the one that reduce the losses. And we want that the voltages and the currents are between the limits. So all the voltages in all the buses are between the minimum and the maximum, and also the currents respect the maximum current in the branches. And so we, what is the mixed interlinear programming model? It is a minimization, because this is a minimization of an objective function that is linear, and all the constraints are linear, so represented by a matrix times a vector equal to something that we know, and or in equality or inequality. And the variables that are the voltage and the current in our case are bounded between the minimum and the maximum, and some of the variables are integer. In particular, for our case, the integers are which are the branches that are connected in the configuration, or which are those that are not connected. The basis of the model is the linearization of the nonlinear function. So you see here that there is a function fx of x in the axis, and this nonlinear function can be represented by So these are the breakpoints. These are these slopes of this linear approximation that approximate the nonlinear function. In our case, the function is not so strange as this, but it is a little bit simpler because it is in general a square. We have the losses that are a function of the square of the current. And also, the magnitude of the voltage can be represented by the square of the absolute value of the voltage. So also these limits can be represented by a square function. So for the square function, it is easy to calculate the slopes and also calculate and represent the breakpoints. Moreover, for the current, specifically for the current, we have a minimization problem. So for sure, if we say that the current or the square of the current needs to be above this, since we minimize the losses, for sure the solution will be on this curve because there is no reason not to increase the current into the so we have that the optimization problem search for the minimum values of the line currents. The current constraints are up and bound, so there is a clear limitation of the current in all the branches, and the model needs to be represented as square function. So all these three allows us to represent the square of the current without including the binary values. This is important because the lower the number of binary values, probably the faster will be the solution. So these are the details of this concept. So the current we have representing Cartesian coordinates, so real part and imaginary part. We have both the square of the real part and the imaginary part, so we take these breakpoints. So this is in the x-axis and this is the y-axis. These are the slopes. These are the y-axis intercept of all these piecewise linear segments, and so we can include this in the model. So this the objective function, the minimization of the losses, is just the summation of these two summations. So for the real part, the imaginary part, where these are represented by this piecewise linear. Yes, the minimization of the losses. Probably I not mentioned that R is the resistance of all the parts. I just want to interrupt. Piecewise linear. So it means that the idea behind this model is that you have a function. In this case, is the square. Instead of representing this with something that is nonlinear, so it forces you to use a solver that is nonlinear. Are not so fast and without performance such as the mixed integer in general. So we approximate with some segments. Oh, I do apologize. Doing. Yes. Yes, we approximate with the here are the breakpoints, so defined by in the x-axis and the point here, and the slopes that are given here. Of these segments. So you can see that there are lines, you see? And all the lines are characterized by a slope and a y-intercept. And if you say that the solution needs to be above all the lines, you see that you are representing the space, you have the constraints that the feasible space for this constraints is this space here. Since the problem is a minimization, you say that all the lines are present, and just to say that the solution needs to be above of all the lines, and since it is a minimization, it will be on one of the lines. And therefore, it is a representation of the square function that we have included in the model. Is it the answer? Fine? Oh. So these are, I have here the fact that these quantities can be positive and negative, so we have included the absolute value because the square is equal for maximum, and so we use the classical representation of the absolute value with these constraints that we have seen also yesterday. So we can go, the important thing here is that some of the branches are not included in our configuration, so we include this binary variable UB that says that if the branch is on, so it is included in our configuration, or off, so 0, if it is not included. You see that by including here multiplied by I max, when u is 0, of course the absolute value that is a positive quantity needs to be 0. For the voltage constraints is not so easy. It is very similar, so also here we can say that the modulus of the voltage of the absolute value needs to be constraints between the minimum and the maximum, but since there is also the minimum is non-convex, we cannot adopt the same configuration, so we need to introduce some binary variables in order to describe the voltage. Here in the implementation we have a trick that the voltage does not vary much in the configuration, the operation of the network. The current can be very high or also very limited during the hour. The voltage in the network, in order to be feasible, cannot deviate so much with the magnitude and also the angle. So we have considered a maximum angle in the implementation of 5 degrees for all the buses of the distribution network. So in this way, the number of binary variables that needs to be introduced in order to have a good quality of the results is very limited. It's just 3 for all the buses of the network. So this is the representation. We have again the square of the voltage because we need to put a constraint of the modulus that can be represented by the summation of the square of the real part and the imaginary part. We have the slopes and of these lines. We have the absolute value, and you see here that there are the binary variables that allows us to select which is the segment that is active in order to describe the voltage in that particular conditions. These two. There is another slide for this subject that this is the complete description of the piecewise linear model with the voltages. So there are the binary variables that I mentioned, and below there are the constraints that says that the voltage needs to be lower than the maximum, and the voltage needs to be above the minimum. You see that is written always as a lower than, but there is the minus here, so you change the sign, you change also the idea, so it is in the same way. So we can represent the minimum and the maximum value of the force, the minimum and maximum value of the voltage in each bus. So this is the representation of the network equation. This is quite simple because the relations between voltage and current, it is linear, and this is just the equation that says that the summation of all the current in each bus, it is equal to 0. The only trick here that we have implemented is that the loads in the distribution network are in general sensitive to the voltage. So if the voltage changes, also the power absorbed by the load changes. So we have included 3 types of loads. In general, we consider this loads that are so-called constant current. So we represent with these 2 constraints the limitation that the current of the load is constant. So if the voltage changes, also the power will change. And then there is PQ nodes in which active and reactive power are constant, and this is the linear representation, since we say that the voltage deviation are small, so we can introduce a small change representation, so small variation of the model that is linear. And we have also the last one. So this is the variation of the current for this sensitivity to the voltage that was included here. And we have also this one that is the PV node, in which we take into account that the fact that the voltage needs to be constant, or at least at the modulus of the voltage, and also the power, but the reactive power is just limited between a minimum and maximum. This is typical when you have a generator that controls the voltage, but in many cases we don't have this kind of distributed generators that fix the voltage in the distribution network. In general, they are considered a PQ buses in which the reactive power can be controlled, but with this equation we can also represent this situation of a generator that controls directly the voltage at the bus. So these are the line equations. I said before, the line equations here are quite simple because since it is written in voltage and currents, they are linear. They are not the usual power flow equation in which, since they are written in power, they have the non-linearities inside. And this is for the real part, and this is for the imaginary part, obviously the resistance, reactance of the branch. And this delta V is included in order to say that if the branch is connected, this constraint needs to be valid. If the branch is not connected, the voltages at the end, at the terminals of the lines are free. And this is achieved by this binary variables. So you see that if this binary variables is equal to 1, this Bn and Bn simplifies, so delta V is constrained. But if U is equal to 0, this delta V, the voltage difference at the terminals, or the slack, is just constrained to this big number. I put just big number, or in another formulation you have just an M, big M method. So if the branch is on, this constraints, it is equal to 0 with this delta V is equal to 0. If it is not included in the model, this delta V is free to be in very, very large. So it means that this constraint is not more forced, it is not there. Is it nice? This idea? This is the basis of this type of models, the so-called big M method.
Real or imaginary, both these constants will be equally, the relationship is more or less equal.
Yes, this is for the real part, this is for the imaginary part. They need to be both included. They need to be, I mean, in order to be true, this delta V needs to be 0.
So these equations are hold good for three-phase lines or only single phase?
Single phase. Can be implemented also in three phase, but for this we have considered just a single phase. Yeah. The problem is already tough for this solver that putting also the three phase in because you are selecting not the particular operating condition, but you are selecting which is the topology of the network in that moment, so which are the switches that are on and off. And here we have considered that all the branches have the switch on and off, so you are selecting this. So in general, it is enough. It's good? Any questions so far? So this is the basis, because after it is we are quite at the end. There is just the radiality constraints. That is something that is easy. No? You say you need to be radial, and instead in the network, particularly when you have the generators, it's not so easy to force to be radial. Sometimes there are loops that are appearing in the solution. If you just force that the number of branches that are selected on in your branch is equal to the number of nodes, excluding the substation, so n-1 nodes, that is the typical constraint. Indeed, if you have a network with large many, it is not sufficient to guarantee that the solution has any loops. There is a model that is presented in the lecture by others, that is this model here, that includes these variables, and you see that there is a trick, because here it is the summation for all the branches that are connected to a bus K, and entering and leaving it is -1 with this equation here that says the number of the bus -1, the variables that says if the branch is on and off constrains this auxiliary variables, this is sufficient. So in general, this coupled with the first one guarantee that all the solutions contains any loops. We have seen in this model that it is sufficient, but the solver takes a lot of time when the network is big. So we have forced another thing. So we calculate before, for the given network, the number of possible cycles. And for all the cycles, the loops into the network, we say that the branches that are in the loop, that are here mentioned in this L, that are, if the branch is on the loop, so LBC says that if the branch is B is in the loop C, so or cycle C, no? And we say that you see the summation for all the branches, and then there is this association with the cycle multiplies the your choice of 0, 1, if the branch is in the loop, and needs to be equal to the number of branches in the loop minus 1. So you open all the loops, because if a loop has 5, I don't know, you have a network like this, and for example, for reconfiguration, you have selected, there is this, I'm not changing the red. You have selected this, you have branch 1, branch 2, 3, 4, and 5, and here you say, okay, all of these are associated with the decisions if it is in the configuration or not. But since these are belonging to the cycle C, the summation of the branches, the decisions of this loop cannot be 5, needs to be 4. So it means that at least one of these needs to be 0, needs to be disconnected. And this facilitates the solution. So in general, it is not true that if you limit the constraints, you have a fastest solution. Sometimes, if you add some specific constraints, the solution is facilitated. Although the first two are sufficient in order to guarantee that at least there is no cycles, there are no loops in your network.
Sir, is there any method for renumbering the branches?
Oh, we have just numbered from 1 to the end, I will see. But there is no, I mean, a link with the method, the solution, so it is, can be anything. The thing here was just to pre-calculate what are the independent cycles into the, so we have just put a method that is known in the literature, that is just a spanning tree is determined by the depth first search. So we have just a search, there are also tools available. We have implemented in MATLAB, so there are also tools for the graph theory that are calculating the fundamental cycles, and then all the cycles are the combination of the fundamental cycles. So it is just a matter of combination, and for a large network we have limited the combination just to five fundamental cycles. So probably this is enough. So we can pass just to the illustration of the examples. Here are the details. So for the representation of the square of the current, we have represented with models of 31 segments, no? So 31 lines in order to represent with a detail all the current. For the voltage, I said that we can limit to 4 because we assume that the maximum phase deviation is 5 degrees with respect to the slack bus. So this is the first illustrative model. This is, you see a network with just 2 squares. This is the substation. This is a generator. And we need to select which is the optimal configuration. I've shown here the optimal configuration that we have found. That is the equivalent of that presented in the literature and can be calculated. So this is known the solution. There are 3 cases. The first case, just this is fixed as a PV node with the 0.97 per unit of the voltage here. In this, we force that Also, the voltage in the other bus cannot be below 0.97. Instead, in the first solution, the lowest it is 0.9. So we forced a voltage test for the solution. And here we put a constraint here for the maximum current that is flowing this branch. And this achieves this solution. So you see here the results, and what is the interesting aspect is that we have also calculated the power flow equation, or the power flow with a separate calculation for the optimal configuration, and we see that the values that are obtained by the power flow calculation, detailed calculation, is quite close. They are quite close with respect to the values that are at the end of our solution of the reconfiguration problem. So although the aim of the tool is not to calculate the power flow equation, but to choose which is the configuration, the power flow that is at the end of this calculation corresponds as a clear link with the power flow of the calculation. No? So this is a good thing. So we can also see the other tests. You see here 15 bus, 32 buses system, 69 bus. These are the typical network that are used for this kind of testing in the literature. So we have compared, and the 83 bus with 96 lines, and this 133 bus with a 156 line system. The larger the system, the larger is the computational time. So I just anticipated the conclusion that we have seen here. But how much is the time in order to with this model? So you see that we are not, changing some parameters on the model in order to adapt to the specific configuration. It is the same model that is running with the different tests with the same things. So you see here the comparison, the quality of the results. So the comparison between the results that we have obtained for the various systems, and for the losses and so on. So we have compared all these things. The configuration that we have obtained, it is the similar of that one presented in the literature, at least at the minimum cost. And I would like to show to you just the last one, in which we compare the various systems. And these are very low value in general, lower than 1%, it is 0.0, 0.1, and so on. And this is the comparison with the power flow calculation for the configuration that was selected. And so these are the number of binaries variables, and without the opening of the cycle, so what I have mentioned here, for the small network, it is not needed. I mean, it is less than 1 second. For the 83 buses, it is 419 seconds in order to obtain the solution, so quite heavy, and also 855 seconds here. And but if you when we include also this opening cycles constraints, there is a clear reduction of the time. For example, 400 here seconds, here it is less than 200. Here was 800 seconds, here it is 100 seconds for this system. So it is, very effective, this kind of things to introduce the constraints that says that all the cycles are open. This was just a focus on the 32 bus system and 69 bus system. But the idea at the end, it is quite the same. So these are just the tape. I don't know if you have any hope. This was in brief the proposed mixed interlinear model. It is one of the methods, but I have already explained why we have done these studies. Determines the minimum loss in configuration. Take into account the typical operating constraints and the presence of embedded generation through a linearization technique that performs satisfactory for all the tests carried out. It finds the known best solution, so we know already the best solution because in the literature there are other methods and so on, and providing the final results that are in reasonable agreement with the power flow calculation without any need of initial feasible configuration. This is also another advantage that probably I didn't mention before, but was clear. It is just we don't provide the initial solution to the solver. The solver starts without any knowledge and finds solution. Because in other methods you need sometimes to say, start with some solution. So the computational times, it is also linked with how good it is the first solution that you provide to the method. The second part was just something very practical in the sense that near to Bologna, they have installed a combined cycle power station, nothing very special. It is, two gas turbines and a steam turbine in combined cycle, and it is, the size is 30 megawatt for almost all the three. So they are more or less of the same size, and so the total is about 80, 90 megawatt. It is included into the city. In order to have the permit to install this power station close to the center of this small city near Bologna, it was required by the municipality that this power station needs to provide some service to the city. And the service is that if there is a global blackout in the high voltage grid, this power plant needs to maintain the service as a backup source of the distribution network, part of the distribution network of the city. So the power station was equipped with some control system and I will try to illustrate this, and I try to illustrate the tests that were done early in the morning in August in order not to avoid to give much disturbance to the city in case something was not good, and by using the phase management units for the monitoring and also for the operation. So I will try to describe a little bit better the system. There are these units with their transformers that are connected with the bus of the power station. So until here, this is the power station here. And there are gas turbines, 32.9 MVA, 33 MVA for the steam turbine, and the other gas turbine is identical for the first one. So you see that is less than 100 megawatt in total. So this bus is 132 kilovolt. There is a cable, 1 kilometer, more or less, to the high voltage bus of a distribution substation. So this is are the transformers that are feeding, they are three, they are feeding the 15 kilovolt distribution network. So here below there are the final users. And this is the high voltage line that connects this substation to the rest of the transmission network. So the tests were carried out by opening this circuit breaker. So this circuit breaker is opening abruptly, and the power station needs to be able to sustain the load. For this, there is a specific controller that when this circuit breaker is open, the active units of the power station, if the power station is not in operation, cannot be sustained. So we expect that at least one or also more of these units were able to operate. The steam unit can operate only if there is at least one gas turbine that is on, because there is no additional firing in the steam generator. So there is a specific control that when this breaker is, a circuit breaker is open, then one of the units, in general it is a gas turbine, the gas turbine takes the role of keeping the voltage stable. So there is a specific control that fixes the voltage and fix also the frequency. So it is not a droop control for the frequency, but it is in high-landed mode, so the frequency it is 50 Hz. It is without any droop. And the other follows. The idea is to install these PMUs, and we have installed these 3 PMUs, two at the terminals of the circuit breaker. So one before and the other after the circuit breakers. So we can understand also from the phasor measurement units when the circuit breaker is open. And the other one at the terminals of this line in order to see what happens directly in the bus bars of the power station. It is a little bit difficult to find the PMUs for distribution networks, because in general for this kind of study and so on, we need some specific requirements that are not in general covered by the PMUs, typical PMUs installed in the transmission network. And since we are involved and so on, we have developed the PMUs in our laboratory, so there were some kind of in-house PMUs and not directly bought from the UT. I don't know if you have any question or any of this, and then I will, yeah.
So this paper it is in 2011, published in 2011.
Yes, yeah.
So at that time PMUs, how it is tested by any?
Yes, we found that was difficult to find the PMUs that are, good for this job, this project on the market directly. So we have implemented something that is not much sophisticated, but it was good for the purpose in the laboratory. Yeah. So it is, probably you all know what is the PMU. So it is a device that measures the voltage. We measure just the voltage modulus and also the angle. So by using the GPS signal that gives the time, the reference for the time. So the results, first example of island maneuver. We have here that the gas turbine 1 and the steam turbine are in operation at this level of the voltage, of the power, 21 megawatt and 81 megawatt for the steam turbine. Was early in the morning, so the load was not so much. So, and the idea was to represent the typical behavior, respectively, so to almost balance the load request of the distribution network. So we have no much flow, power flow in the connection to the high voltage network. And so we open the circuit breaker, and this is the power management of the power station, or the disconnection of 2 distribution network feeders for a total load of 2 megawatt. So in this case, this is the configuration. These are the position of the PMUs, and this you see the frequency here, and this is the stable frequency in the system, and here the frequency in the islanded condition of the distribution network. And this was a good thing for us to see, because this corresponds also to the measurement of the speed of the turbine in the power station. So we can compare the accuracy of the PMU with respect to the actual measurement of the speed in the substation. Obviously, the speed is increasing, but you see that the gas turbine is able to control the frequency. Obviously, it is not exactly the same frequency of the network. And these are the measurement of the angles. So this is the angle here. Until here it is the connection, and then here we open the circuit breaker. So this is the angle between the two phasor measurement units that are at the terminals of the circuit breaker. And you see that the angle it is increasing because the two networks are not more synchronized. And these are the angles between the phasor measurement units at the terminals of the cable that connects the power station to the distribution network. So you see that they are connected to this cable, so they are close. No? The idea was also to identify how much is the power in the cable by using this information. It is not very accurate. Probably we need to do so. But this was the idea. This is the amplitude of the voltages, so at the disconnection this is in the network, and the other two are in the islanded distribution system. You see also here the effect of the excitation system, control system of the voltage in the power station that keeps the over voltage. It limits in few seconds, less than 10 seconds, the voltage in the distribution network. So the voltage control is probably more is faster than the frequency control. Yes, it is, because the PMU is, focus on there is a filter at the beginning, there is a trick in order to not, it is disturbed, so there are harmonics, so you need to identify what is the first component, so the 50 Hz from a waveform that is contains also some harmonics, some disturbance. Yeah. Another islanding maneuver was this one, that the gas turbine was in operation at an output level of 29 megawatt with a positive export to the external network equal to 1.9 megawatts. So there is overproduction, and so the gas turbine and steam turbine were in standby. So there is the intentional opening, and the system remains stable in operation. The gas turbine output was around 27.3, so it is decreased, and the frequency is maintained about 50 Hz. So this is the frequency. You see this. This is also the comparison with the SCADA, the machine speed in this case, and then these are the angle between the PMUs at the terminals of the circuit breaker, and these are the PMUs in the terminals of the cable. So you see some difference, but it is limited. this is the amplitude of the voltage and operate the disconnection, no, but the reconnection, so a monitoring, because in that case, the operator of the power station becomes like an operator also of the distribution network, because it is an island in which this power station is the main supplier of electricity to the distribution network. So the idea is that, these informations were also provided in the control room. So you can see here the reconnection, so angle difference. And you see here the idea is that when the angle is approaching to 0, then here there is the reconnection. So the operator in the power station can also have an indication when to close the circuit breaker BR1, because there is no, another possibility, no, is the main provider of this service. So there is this idea, and is closing here, so the circuit breaker is closed here, and these are just the angles between the two in the cables, and you see here the frequency, and the frequency is, this is the frequency, obviously this is the frequency in the high voltage, that is very stable because it is connected to the European network, so it is all the European. So it is quite stable, and this is the frequency inside the island distribution network, that you see that, there are not big variation, but it is, there is some activity there. And here it is the point in which there is the reconnection. Obviously, the angles are equal, but the frequency is not. So obviously, the power station of 100 in this case 30 megawatt cannot change the frequency of the entire network. So it is the frequency of the isolated network that is going to the frequency of the external network. And these are the voltage phasor amplitudes. So you see here that these are the magnitudes of positive sequence components for the two PMUs inside the islanded network. This is the PMU connected to the high voltage network. This is the point of reconnection. They are working together. There are some also measurement errors and so on, but it is quite accurate here. And probably have reached the final. If I can add a very small thing, is that during this test there was also a fault, because in order to do this we needed to open the distribution network. I was also played, and we opened, no? So the distribution network was distinguished with respect to the distribution network that was not affected by these tests, no? And when you are in island, the voltages at the terminals of the circuit breaker in the substation, in general, the voltages are angle 0, no? So they have the same voltage. But if you open the circuit breaker and this part of the network is in an island condition, this voltage has a frequency that is different from the voltage in the network. So there is a condition in which the voltages at the terminus of the circuit breakers are in opposition. In general, the circuit breaker can sustain the double voltage, the double rated voltage, but one of the old circuit breaker did not succeed. So there was a flash in the circuit breaker in the substation. with respect to this. So and this was something also that we keep in mind with the other test, was that if you want to use in a flexible way the distribution network, also the components probably needs to be updated. You cannot leave a circuit breakers that are there for many years, because probably if it is flexible, you can modify also the operating condition, and so he has a stress that he has not seen in all his life, because never have seen the voltage doubled at the terminals. This concludes this part. I would like to give the floor to Professor.
We have two cases. One is with one gas turbine and one steam turbine. And
Yeah.
Another one is with only one gas turbine.
Yeah.
So, is there any other cases that was tested? Or?
Yes, I mean, in these conditions, in these days that I was there and so on, in order to have this certificate, we have limited to this, because if you put all the two gas turbines, also the steam turbine, you inject a lot of power to the network, because they were from 3 in the morning to 5 in the morning, 6 in the morning. So this was the range of the hours that in some consecutive days were allocated for this, in order not to disturb the thing in so on, the city and so on. And so was limited for that. Yeah.
Basically, what is the voltage level in Italy integrated PMUs? Is the considered voltage level in physical PMUs integration?
In distribution network, they are not much used in the distribution network. They are very common for the transmission. So in transmission network, there are, I think, more than 30 or 50. I have this number of stations, of I mean, we can say buses of the transmission network. Particular are 400 kilovolt, particularly near to the border to the other networks that are equipped with this monitoring system based on PMUs. But in distribution network, until now, the use of PMUs is quite limited. So I'm not aware of many applications. Probably you know better. Yes, so this was the idea. Thank you so much.